So we talked about the fact that an integral is the area under the curve or the area between the curve and the x-axis a long time ago when we first started talking about integrals. But one thing that I either briefly mentioned or said, we'll talk about it later, was that when the curve is partially below the x-axis, right, the integral, let's say from a to b and b to c, the integral from a to b, where we're above the x-axis, right, the integral value is greater than 0 because we're above the x-axis. But from b to c, the value of the integral is less than 0 because we are below the x-axis. And so when we talk about finding the area, not just the integral, but the area between a curve and the x-axis, we have to take into account the fact that sometimes our function might cross through the x-axis. And so we can't necessarily just integrate straight away from a to c. Because if I integrate from a to c, I'm going to get some positive and some negative. They're going to cancel out. I'm going to get something that's a lot smaller than the actual area underneath the curve, area between the curve and the x-axis, which is all of this value. So I need this bottom part that's below the x-axis to become positive. So what we do is we split it into two integrals, one from a to b, and then one from b to c, but we take the opposite of the one from b to c. So as we look for areas, what we want to do is first graph it, make sure it's continuous, and then find any places where it crosses through the x-axis. And so if we have any holes in the graph, any places where we have discontinuities, or places where it crosses through, we take each of those pieces and do them separately, and then add all the areas themselves together. Does that make sense?
So when you're integrating from b to c, you said you wanted to make it positive. Did I hear that right?
So we'll integrate it, we'll get a value that's negative, and then we'll just flip the sign of it to make it positive.
But why would we want to make it positive if it's a negative value?
Well, because we're talking about the area, and the area between
okay.
curve is always a positive. It can't have negative,
I see.
right?
Oh, okay,
yeah. Is a positive value.
Okay, I didn't make that connection.
Okay. Good?
Yeah.
Everyone good now? Any other questions on that? Okay, so let's start with a nice easy one. Let's talk about the function f of x equals x squared plus 1. So we want the region bounded by that and the x-axis, and x equals 2 and x equals 5. So the first thing we'll do is we will sketch this graph and find this region. So first off, x squared plus 1, you should know what that looks like, right? It's just a parabola with a y-intercept of 1 opening up. Right? We should know what x equals 2 looks like, right? X equals 2, it's just a vertical line, and there's x equals 5, just another vertical line. And so if we want the region bounded between x squared plus 1, x equals 2, x equals 5, and the x-axis, we are talking about this region in blue right here. So are any portions of that region below the x-axis? Does my function cross through the x-axis ever? Like my upper limit of my region, my x squared plus 1?
No.
No, so nothing's below it. So this is just as easy as can be, a simple little integral. This is just the integral from 2 to 5 of x squared plus 1 dx. Nothing different than when we were doing our integrals before. We'll recognize, though, that now we're talking about the area between x equals 2 and x equals 5. And what does that give us? It gives us x cubed over 3 plus x, evaluated from 2 to 5, which would be 125 thirds plus 5 minus 8 thirds plus 2. And what does that come out to be? 125 thirds minus 8 thirds ought to be 117 thirds. And then plus 3 ought to be 126 thirds, which is what? 42. And since we're talking about area, we will say 42 units squared. Good or no?
Good.
Wonderful. All right, let's do another one. So let's see if we can find the area of the regions. Looks like we got multiple regions now between x squared minus 2x minus 3, the x-axis, x equals -2, and x equals +3. So first off, we're looking at the function x squared minus 2x minus 3. That one's not as simple as x squared plus 1. How do we graph this parabola?
You can factor it.
All right, factoring it will give us the x-intercepts, right? That's convenient. So if we factor it, it's x minus 3x plus 1 equals 0, which tells us that it has x-intercepts at 3 and -1. So here's -1, here's 3. But also, we know that the y-intercept is -3. We got a point here, we got a point here, we got a point here, and it opens up. And so this is not our minimum point, so we're going to go down like this and up like this. Do y'all agree with that?
Yeah, it looks about right.
Okay. But we want the area between the x-axis and the curve from -2 to 3, which means that we've got a section that's above the x-axis, and we've got a section that's below the x-axis. Good?
Yeah, it makes sense.
Okay, so we'll have to split this into two. We'll have to do one, that's the integral from -2 to -1. What was our function? X squared minus 2x minus 3 dx. And then we will have to do what? We'll have to also find the integral -1 to +3 of x squared minus 2x minus 3 dx. And instead of adding these two things together, I need the opposite of the one in blue, right? Because it's below the x-axis. So we'll put a minus sign there and say we're going to take the first integral minus the second integral. And minus a negative should turn that into a positive. Everybody good there?
Yeah.
Okay. So our integral should be x cubed over 3 minus x squared minus 3x. We're going to evaluate it from -2 to -1 and then subtract. Same thing, right? It's the same function, so it's still x cubed over 3 minus x squared minus 3x, except this time from -1 to 3. And that ought to give us what? -1/3 minus 1 plus 3 minus, this will be a -8/3 minus 4 plus 6. And then we will subtract all of this. 27/3 is just 9 minus 9 minus 9. And then minus, this will be a -1/3 minus a 1 plus a 3, just like we had to start with. Everybody agree with that?
Yeah.
Cool. All right. So this is where things get a little bit messy sometimes because you got minus and minus and minuses and a bunch of other crap in there. So let's just be careful with this here. First off, -1/3 minus 1/3 plus 3. That's -1/3 plus 2. So -1/3 plus 6/3 would be 5/3. And then we've got -8/3 minus 4 plus 6. So that's -8/3 plus 2, which would be -2/3. So we got minus -2/3 or plus 2/3 for the first part of this. Then we've got minus, and then we got 9 minus 9 minus 9. Oh, that's -9. And then we got minus all of this, which is -1/3 plus 2. Again, and -1/3 plus 2, like we said before, was 5/3. So we got -9 minus 5/3. So that gives us 7/3. And it gives us, what is that? That's -27/3 minus 5/3, so -32/3. So minus -32/3 will be plus 32/3, or a final value of 13 units squared. Good or no?
good. Yeah, it just got ugly at the end there with all those fractions.
Yeah, I guess. Any questions on that? All right, let's do one more. Actually, we got like 1 minute. We'll skip this one or wait on this one for tomorrow. We'll just do those first two. And then tomorrow we will continue with this and talk all about area for the rest of the day tomorrow. But hopefully conceptually that makes sense. I'm going to put up a homework assignment that has some area problems. You will not be able to do all of them yet, but you should be able to do a couple of them. It also has some of the accumulation problems where we had like a rate and we had to integrate the rate to get the actual amount that we did sometime last week. So look out for those as well on there. First couple problems will do those.